I'm going to start by saying a huge thank you to IABSE for this award. It really is a huge honour, and I'm certainly very humbled to have received the Milne Medal for 2022. I'm going to use the opportunity to talk a little about some of the projects that we've delivered within COVID, and the title of my lecture is More for Less, and I hope I'm going to illustrate what I mean by that through the course of the presentation today. I joined what was Flint and Neil and has now become part of COVI in the UK a little over 20 years ago. At that time, it was a partnership run by Ian Firth and David Mackenzie. It's now part of a much bigger organisation. But I think the philosophy that Ian and David brought or had with the organisation and brought through into COVI still remains very firm. And I think it can be summarised as follows. And indeed, preparing for this lecture was a very good opportunity for me to condense my thoughts in this regard. I think we try to bring an holistic, whole life approach to all of our projects. We like to add value, and that's not just monetary value, that's adding value in lots of different regards. Design quality has always been at the forefront of what we do, and that's a philosophy that's very much been promoted by Ian Firth, and I think is best summarised by his Institution of Structural Engineers address, presidential address just a few years ago. We work with architects on a great number of our projects, and I think that again is an extremely important way of adding value. That collaboration is really key to what we do. Sustainability has always been at the heart of what we do. I think the last few years have seen that condensed into a real focus around embodied carbon, but I think again that is very, or rings very true to what we do. We do an awful lot of work with contractors, and the very simple metric that many contractors use when assessing the cost of projects is to look at quantities, and of course there's a direct correlation between quantities and carbon. So I think cost is a proxy for carbon in many regards. Ease of construction is of course hugely important to what we do. We do a huge amount of work for contractors, again in the design and build space. We've developed a very good appreciation of construction methods, construction techniques, and also what drives contractors, what's important for contractors in terms of construction methodologies, and that is very much at the heart of our philosophy. And then longevity and low maintenance requirements. That I think flows very simply from the fact that a huge proportion of our work is, the firm's work is on existing bridges, and that very much informs our new designs. The past informs the future, as it were. That knowledge of what goes wrong with existing structures is gold dust in terms of informing good design for the future. So I think then in terms of design approach, we work closely across our offices in the UK and our offices in Copenhagen, North America and South Korea. And that, as much as anything, is driven by the very substantial resource requirements for some of the bigger projects. I'm going to talk about one of those today. That collaboration across offices is also a golden opportunity to share knowledge and methods and approaches. I think in some respects there's an essence of competitive rivalry there, but when harnessed, that is incredibly powerful. We like to be brave, we like to question, and we like to challenge. I think the challenge can sometimes be a little irritating for some people, but it really is key to achieving the maximum, more for less. We are naturally, I think, curious. We like to push boundaries. We don't like to necessarily do things as they were done before. We like to ask the questions about how things could be done better. We like to provide opportunities, and that's opportunities not only for our own staff to gain experience, but also to explore opportunities for our clients. And again, I'll try to illustrate that in a moment. We rely very heavily on a set of specialists across many different skills. And again, I'll explain by way of a few examples what I mean by that. But having those specialists, and they really are world-leading specialists, I believe, is key to delivering some of the complex projects we get involved in. And we like to co-create. And when I say that, I mean we like to engage with our client, understand our client's needs and wants. As I've already touched on, we like to work very closely with architects. We see the value they build. And again, we like to work with the contractors who are going to build the structures, the bridges. Last but not least, we like to work with the operators. That is the people who are going to operate and maintain the bridges, the structures through their life. That is key to informing good design, I believe. We work across the globe. We have, as I said already, we've got offices in North America, Scandinavia. We have offices in India and the Middle East. I'm today going to present a small selection of projects to illustrate my 20 years or so with Covey. Those particular projects are in the UK. I have a project in France. I have another project in Bangladesh, which is of a quite different nature. And then last but not least, I've got a project which we've been working on most recently in Australia. So the first project I'm going to talk about is the Sail Bridge, otherwise called the Port Towie Bridge in Swansea in the UK. This shows the completed Sail Bridge itself. The scheme itself was to deliver 2 bridges and a walkway connecting the 2 bridges. The 2 bridges can be seen, or at least the client's initial proposal for the bridge locations are shown by the white arrow at the top of the screen at the north end and the arrow across the river at the south end. I think this project nicely illustrates the collaboration with architects and the focus that the architects bring in terms of the place setting of the bridge, and that long-term, that timeless view of the value of bridges. Having visited the site here, it became quite apparent that the client's proposed crossing location, where the white arrow is shown, was, shall we say, suboptimal. It was right outside a very large supermarket, and it crossed onto the east side into a quite uninviting location, whereas having visited the site, it was quite apparent that by moving the crossing location a little further south, it provided a fantastic opportunity for a much more suitable landing positions on both the east and the west bank, and the opportunity for a much more dramatic structure. So this was my first experience of working closely with architects and really starting to appreciate the value that they bring to projects such as this. And I was very fortunate to work with Jim Eyre, who heads up Wilkinson Eyre, together with Martin Knight and Ben Addy, who I've gone on to work with on many other projects through the years. So to summarise the setting here, you've got the Dockland area on the east side, that's the right hand side as you look at the screen, connecting with the town centre on the left hand side, and the 2 bridges were really to provide that connectivity to the Docklands area. This is the design that was developed for the Sail Bridge. This was very closely developed by Wilkinson Eyre and ourselves. The cable stayed bridge itself consists of a 42-metre high steel mast which is leaning backwards, with a gently curving deck which is supported off one side by a series of cable stays. Structurally, it's quite a unique configuration, I believe. You've got the deck cross section, the stays here on the left hand side. You've got a steel box, a stiffened steel box with cantilevers projecting on the right hand side, supporting a deck that consists of aluminium deck planks. And that was very deliberately to help segregate pedestrians and cyclists. A great deal of effort was put into detailing of the parapets, both on the upstream and downstream. Really, on the downstream side, the focus was on creating a structure that was very open to promote good views from the bridge looking downstream. And here's to illustrate the importance of the specialists. So I should explain that the whole project was developed under an early contractor involvement scheme, an ECI scheme, and it was developed at quite some speed. And I remember going to EM one day when the bridge was already in fabrication in the fabrication works at Rocourt in South Wales, saying, "Look, Ian, I think we have a problem with the dynamic behaviour of the bridge, because the lateral mode of vibration coincided quite unfortunately with the peak lateral mode of vibration." But fortunately we had the expertise in-house at that time within Chris Barker to advise on exactly how we suppress these dynamic problems. And the solution actually was quite simple. It was to introduce some tune mass dampers, which is what you see here on the right hand side. But this example I included just to illustrate one aspect of the importance of specialists. The second one, again involving Chris Barker as one of our key specialists, was wind tunnel testing. So we put a deck section model in a wind tunnel at BMT to establish its aerodynamic stability. And as you can see by the video on the top right hand side, unfortunately we experienced some low speed vortex induced vibration, which here you can see the bridge deck oscillating in the vertical direction. Again, the bridge deck was in fabrication, so our options were fairly limited, but Chris Barker fortunately stepped into the wind tunnel, and you can see a wooden stick on the bottom right picture holding up a moulding that was used to change the profile of the leading edge of the bridge deck. And this was typical of how Chris went about trying to solve the problem. He investigated changes to the shape of the bridge deck cross section to effectively get rid of the vortex induced vibration. And very quickly he came to the conclusion that actually by adding an aerodynamic fairing on the upstream lower edge, which is what you can see here in this photograph, provided a very effective means of suppressing the vortex induced vibration. It works effectively by preventing the flow detaching quite so soon, and that effectively suppresses the vortex induced vibrations quite adequately. We were still at a point in the fabrication process where we could detail, in this case, these stainless steel fairings and have them fixed on the upstream edge, and it was quite a neat solution. This photograph also gives you a good appreciation of the parapets, in this case all stainless steel, all very carefully detailed. And of course that's very important because the user experience is all around the quality of those finishes. Now to talk about the construction. Again, this goes back to one of the key philosophies I spoke about earlier on, and that's collaboration with the builder. So the mast itself was actually quite a complicated geometry. We engaged in very early discussions with Rocourt, the fabricator, to understand what was and wasn't possible. Basically, the mast geometry is defined by a series of flat plates. There's no warped plates, but by careful sculpting on behalf of the architects, we were actually able to come up with this fantastic looking mast geometry. Here you can see it in fabrication. On the right hand side you can see one of the upper sections of the mast. You can see the stay anchor plates projecting like ears from the top edge, and on the bottom edge, which is the back facing edge of the mast, you can see a triangular section which is quite large profile section that forms the V-shaped tail of the mast itself. Here you can see the mast at a slightly more advanced stage of fabrication. in the works here. You can see all the welders inside welding up the stiffening around the diaphragms. This was then to show the erection of the mast. The mast itself weighed around 80 tons, and it was erected using a crane position with a lift radius of around 80 meters. And at the time, this was one of the largest mobile cranes to be used in the UK. But it was felt that by erecting the mast as one completed unit, we ensured both better quality of construction and also a faster construction program, and that was one of the key aspirations of our client, the Welsh Development Agency, and that approach was developed in conjunction with the contractor Balfour Beatty. Now, I did mention at the beginning that the Sail Bridge was one of a pair of bridges. The other bridge was what we called the Barrage Bridge. That crosses, not surprisingly, over the barrage, somewhat further south. It's not necessarily the most hospitable of locations, but the real eye-opener here for me was that even though this was a secondary bridge, it was still given a significant degree of care and attention in terms of detailing. In fact, in this photograph you can see the Barrage Bridge and you can see the Sail Bridge in the background. But again, working very closely with the architects, they showed me that by carefully modifying the geometry of the Warren Truss, you could actually come up with something that was reasonably attractive, even if it's a low-cost solution. I think you probably agree that it's quite an elegant structure, even though it's quite modest. It's around a 70-meter span and it's around 5 meters wide. And the view on the right-hand side gives you a bit of a feel for the user experience by inclining the mast, by inclining the trusses inwards. You enclose users, you create a safer feel for users, and you increase the structural efficiency by stabilizing the top chord using those simple transverse bracing members. The next bridge I'm going to talk about is the Schumann Bridge in Lyon in France. This was a project we won through a design competition with Exploration Architects, a Paris-based firm of architects we've had a very successful track record with, together with consulting engineers Agibat from France. And our role in this team was to design the superstructure, that's the deck and the arch, as well as leading the design team overall. This was a hugely challenging project for me personally, because slightly embarrassingly, I don't speak French. I managed to attend numerous meetings over the 18 months or so that the design period lasted. I managed to understand enough of what was being said, even though I struggled to reply. But the bridge itself is located adjacent to a UNESCO World Heritage Site in Lyon. And for that reason, enormous focus was placed on the appearance of the bridge, not surprisingly. So this is to show the overall geometry of the bridge. You've got main spans of around 85 meters. We decided very early on that we didn't want any cable stays, we didn't want masts. We wanted a very flat structure that was very as near invisible as possible given the setting, and yet with a fairly significant span that does introduce a challenge. So this led us quite quickly towards the idea of a very flat arch. The geometry of the bridge is very much driven by the limitations on construction depth for the deck. That is that we squeezed the deck is squeezed between the navigation envelope for river traffic below and the constraint driven by the gradients on the bridge and the tie-ins at both ends. And that really greatly limited the construction depth that was available to us. So as I say, the solution was this wonderfully slender arch. In cross section here, you can see the very shallow deck only around 600 millimeters deep, and you can see the arches inclined and leaning outwards. We used the arches to actually separate pedestrians from vehicle traffic, and I think again that adds something quite special to the quality of the design. Again, this is the perfect example of that very close collaboration with the architects. There was a drive to create these nice wide footways and to create places that people want to stop and rest and enjoy the fantastic views up and down the river. So besides having this wonderfully slender arch that's unbraced, the architects wanted to exploit the arch's ability to reflect light by creating a twisted profile to the arch. To the best of our ability, to the best of our understanding, this is the first time this kind of design has been developed. It's done on the face of it in a very simple way by taking what's called WP3, that's the outward pointing edge of the arch, and moving it up, as you see here, as you go from section A to section B to section C, moving that point up and then back down. And that means that the two primary top and bottom plates of the arch are warped, they're twisted, whereas the inside face of the arch is maintained on a constant plane and there's no twisting there. So key challenges here for us were, first of all, how do we design the arch for such a twist? There are no design rules available for such a variation. And then secondly, could it be fabricated? So in terms of the fabrication, we went to Victor Boyk, the fabricators, had some very early discussions within the design period with them about how this could be done. They were very confident it was feasible and gave us some fantastic advice. Then turning internally again to one of our experts, this time Chris Murphy, one of our steelwork experts, we asked him to develop a design philosophy for these twisted plates. He went away, came back with a proposal which basically revolved around ensuring each of the plates is effectively a class 3 section, so he's able to develop its full yield capacity. And that was the approach we set down, and indeed it was proven to be very successful. I should mention at this point our project manager Ollie Stross, who I worked very closely with over the period of developing this design, and I think Ollie's a great example of how we as an organisation have provided those opportunities to our up and coming engineers to develop. This view shows the completed arch, and I've included this because it shows wonderfully well the twist on the arch. You can see there how the light reflects differently as you move along the length of the arch. So the fabrication process itself, here you can see a section of the arch being fabricated by Cordioli, the Italian fabricator, who eventually won the contract. And I think the wonderful thing here for me is understanding the whole fabrication process, and particularly working with their very skilled craftsmen, I would call them artisans, who were able to introduce the twist that we wanted to the arch. Now that twist it's actually relatively modest. It's about 1 degree per meter length as you move along the arch. But the twist is introduced, as you can see on the right hand side, by heating the arch or the plate in certain locations. So the process is effectively to force fit the first 2 plates on the left hand side, and then the closing plate you heat and you force into position, and the striations you see on that plate are a result of the localized heating to introduce the deformation that's required. To enable construction of the bridge, we identified a port on the south end of Lyon that was available for pre-assembly of the bridge. Now this was because there was insufficient space available at the bridge location itself. However, the port was made available. The challenge there was that we had to navigate from the port to the final bridge location, where the yellow pin is, navigating under some 15 or so existing bridges. In order to do that, the contractor Cordioli developed this fantastic mechanism here. You can see on the top effectively what are two enormous hinges which are used to allow the arch to rotate from a flat position up into its final orientation. And on the cartoon sketches across the bottom, they're to illustrate the system whereby you have a jack that rotates the arch around and uses a series of locking pins to secure it at each increment. It really was a remarkable system. Here you can see it being trialled in the dock before the bridge is moved out. Here's a view showing the bridge being moved up the river. And indeed, it passed under one of the bridges with only around 150 millimeters of clearance. But this was all surveyed in advance, so we were in fact confident it was going to work. But it was nevertheless somewhat nerve-wracking for Ollie and myself, as the two spans were navigated upstream. And I've just got a video here, time-lapse video, showing construction of the bridge. This starts in the port. You can see the two spans being assembled. You can see the arches being rotated down into the horizontal position. The bridges were then moved out onto a barge using SPMTs before they were floated upstream to their final locations. The two spans were moved in different operations around 2 or 3 weeks apart. And I do love this video because you start to get a bit of a sense of the location itself and the challenge of navigating each of these bridge decks upstream. So the bridge actually was fabricated and moved, transported without the concrete deck. The concrete deck itself was poured in situ. I should say the deck itself consists of a series of steel transverse beams with concrete cast around. It's what we call an infill deck. This is the second span being erected in exactly the same way. You can see some temporary bracing used to stabilise the arch there. And you've got this wonderful shimmy of a movement as the second span is brought in and gently lowered onto its bearings. And just a couple of views here to show the completed bridge. Again, I love the lighting on these photos, and it does also give you a bit of a sense of the space available on the bridge deck for pedestrians and bridge users just to stop and enjoy the fantastic views both of the bridge and of Lyon itself. I'm going to use Lyon as the first example to talk about something I mentioned earlier on, and that's embodied carbon. Now within COVI we are fortunate enough to have a fairly substantial database of bridges that we've designed. They're of a variety of different construction forms. Ultimately, most of the bridges are beam and multi-span bridges because that's by far and away the biggest demand. But we do have some arch bridges, some cable stay bridges, some truss bridges and suspension bridges to throw into the mix. And full credit here to Cameron Archer-Jones and Dan Green for developing this database and for developing a series of tools that we now use readily to assess the carbon content of our designs. I particularly like the histogram in the center above on this plot because it provides a very useful overview of the differences in carbon content between the different forms of bridge. That's the arch, the beam, type bridges and so on and so forth. And I think that's quite important to remember. I'm going to come back to that as we progress further on. So Cameron and Dan have written a paper which revolves around what they call the Scorbs assessment of bridges. So this is measuring embodied carbon in bridges and coming up with a bridge rating system. I'd really recommend everybody to read it. It's fantastic. So the idea here is that in the same way that is done for white goods and is done for buildings now, you rate the carbon, the embodied carbon for the bridge, in this case A to G. Now it's worth remembering here that for bridges such as arch bridges, as I illustrated on the previous slide, inevitably the embodied carbon for some forms of construction will inevitably be higher, and I think that's probably quite nicely illustrated by the example of Schumann Bridge here, which doesn't score particularly highly, but is around about an F. But I think it's best to tell it like it is. This is an honest view of where we're at. The next bridge I'm going to go on and talk about is the Mersey Gateway Bridge in the UK. This has been by far and away the biggest project I've worked on. And at one stage within COBE, we had around about 100 engineers working full time on it. So the scheme itself is to provide a new crossing upstream of the existing Silver Jubilee Bridge, which you can see here in this view. The red line shows the approximate location of Mersey Gateway Bridge. Key constraints here revolve around the salt marshes, the Ramsar site, which is downstream, that's a designated wetland, and a triple SI. And so I've included this example for several reasons, but when we talk about more for less, then the key thing here is working within the environmental constraints. Now the constraints in fact were fairly wide-ranging. There was quite an industrial legacy associated with the area, which has resulted in significant contamination on the bridge site. I'm not going to have a chance to talk much about that today, but that certainly drove a number of key features of our design, again where we worked very closely with the contractor and with the likes of the Environment Agency. The environmental constraints I've already touched on. They actually determined that we could only locate foundations in what were termed some grey zones within the river itself. I'll come on to that in a moment. That effectively drove the design towards being a cable stay bridge solution. We crossed the Manchester Ship Canal and the St Helens Canal. Aesthetics were a key feature of this project, and I think there's a wonderful example here because the client, Halton Borough Council, were sufficiently well informed to engage night architects to advise them on bridge aesthetics, and that had a significant bearing on the solutions that were eventually developed. Windshielding was required in order to prevent the bridge being closed in high winds, which is a problem that's been encountered by the Silver Jubilee Bridge. So this was all about providing robustness around the transport corridors. And of course, being a concession contract, rapid construction techniques were critical, and that's because the bridge doesn't start collecting revenue until it's open. So clearly getting it open to traffic as quickly as possible is paramount. So one of the key features, one of the key constraints of the project is actually the very dynamic nature of the river. And I've just included this slide to show migration of the principal channels back and forth across the estuary over a number of decades. And one of the key requirements of the design solution that we provided was to avoid inhibiting in any way the migration of those river channels. So as part of the optioneering in the tender stage, we developed a series of solutions for the main crossing. That's the cable stay bridge crossing, which is shown here. The final preference was actually to go with a large single cell box and to have mono towers, that's single columns for the towers. That was primarily because mono towers enable a much more rapid construction process for the towers themselves when compared to building inclined tower legs or even two tower legs. However, the fact you've got a mono tower really dictates the fact you need a torsionally stiff box for the deck itself, which is why that particular solution was proposed. The choice was made to cast the bridge deck in situ using the balance cantilever technique, and I'll come on to explain a bit about the construction process in a moment. And then a similar exercise was undertaken for the approach viaducts. The approach viaducts are actually about 1.2 kilometres long in total altogether. Here we looked at a number of different solutions, and there was a big focus in terms of making sure that we had continuity of bridge deck edge details, and that was that eventually led us towards a single cell box, as you see here in this view. However, in this instance, the construction method is really quite different. We're using what's called the movable scaffold system for construction of the approach spans, and I'll come on to explain a bit more about that in due course. There was a decision. So in terms of the option selection criteria for Mersey Gateway, program was of course key. The faster you can build the bridge, the more toll revenue you can collect, because the concession period starts from the moment you sign the contract, so i.e. before construction starts. Maintenance is key, and the real thing to emphasize here is that the bridge operator is able to inform the inspection and maintenance regime they want right from the beginning of the design process. And I think that goes back to a point I touched on at the beginning about the importance of longevity and reducing maintenance costs. Capital cost is of course always important. Aesthetics I've touched on already as being a key aspiration from the client side, and we engaged Dissing and Weitling to be our architects. We've worked very successfully with Dissing and Weitling on a number of projects all over the world, and they worked integrated within our design team to develop the solutions. Past experience from the contractor's side was a big factor in determining their preferred solution, and in particular they favoured in situ concrete construction. That was partly to reduce the maintenance costs associated with repainting of steelwork within the concession period, but the choice for in situ came really because the size of the scheme means it's not economic for precast segmental construction. So the philosophy here is to take the factory to the work front and maximise the use of repetitive in situ construction cycle times, which really requires early gain of concrete strength. And again, that's something I'll touch on in a moment, and avoiding the use of marine plant. So here you can see an elevation on the main crossing. That's the cable stay bridge. It's about 1 kilometre long. You've got 3 towers. You'll notice, of course, that the central tower is significantly shorter than the outer towers, and that was primarily driven by the fact that we weren't permitted to put anchor piers in the back spans here and here, which is what you normally try to do with a cable stay bridge. We were restricted to having the pylons in what we call the grey zones, which are shown here, here and here. I referred to those earlier on. And we've got a modified harp arrangement in terms of the stays themselves. This shows the north approach viaduct. Spans are of the order of 70 metres. We managed to make some fairly drastic simplifications from the client's reference scheme, which actually had a series of independent structures spanning across the north here, and turning it into one continuous viaduct over its entire length. And then similarly on the south viaduct, we managed to make some simplifications there. You can see here where we cross the Manchester Ship Canal, and we lead on to what's called Asmore and Bridgewater Viaduct on the south end to the right hand side here. Again, spans of the order of 70 metres. The bridge deck cross section itself, we've got enough space for 3 lanes in each direction. You've got the space down the middle for the pylon, at least in the cable stay bridge section. You've got steel delta frames here inside the cable stay bridge section of the box, and generally speaking you've got ribs at around about 6 metre centres supporting the concrete deck slab. In fact, one of the real features in terms of pushing the design is the fact that the 250mm thick deck slab is spanning some 6 metres between these ribs, but spanning 7 or 8 metres transversely as well. So we're working the deck slab quite hard. In terms of a breakdown of what the bridge deck cross section looks like, every part of the bridge deck cross section is designed to be optimized really around not only structural performance and minimizing quantities, but also buildability. And this cutaway, I think, illustrates a few points worth touching on. So you've got these fabricated steel delta frames you can see here. On the ends of those you've got precast anchor blocks, and those are deviators and anchor blocks for the post tensioning. They have quite dense reinforcement in, so there was a significant advantage associated with prefabricating those and lifting them in already cast. Given their complexity, you've got transverse post tensioning running through the deck slab, and that's to minimize the thickness of the deck slab and to make it span, as I described in the previous slide, over these fairly large bays. On the edges we have precast anchor blocks, and that's primarily to allow us to stress the transverse post tensioning as early as possible in the construction cycle, when the concrete is still quite young and still gaining strength. And the advantage these give us is that they distribute the forces from the anchor block over a much larger area. Here you've got precast fascia beams along with all the rest of the deck finishes. The pylons are fairly conventional. You've got a fabricated steel box on the inside with in situ concrete cast around. The tallest of the pylons rises around about 100 metres above deck level, and it's only 3.5 metres wide in this elevation. So the pylons are actually remarkably slender. The articulation of the bridge is quite unique in the sense that the approach viaducts and the cable stay bridge are continuous, and the only place you have the expansion joints are here and here. And the real advantage there is the simplification of the articulation and the elimination of expansion joints and all of the problems that go with the expansion joints. And again, that harks back to what I discussed earlier on about the importance of maintainability within our designs. That did create a challenge in terms of how we analysed the bridge, because it meant that we had to have one model for the entire bridge, and this is to show our global model here. The articulation is such that all of the longitudinal forces are actually taken on the centre pylon, and as a result you have some fairly substantial, we have the highest bending moments appearing at that pylon. However, that pylon actually has the lowest overall vertical reaction, which created some challenges in the design itself. We had to undertake aerodynamic testing of the bridge deck cross section, and that was to prove both the aerodynamic stability of the bridge deck and the performance of the wind shields themselves. You can see the wind shields in the left-hand photograph. And we also undertook testing of the pylon itself. You can see the pylon in a wind tunnel here, where the wooden blocks are being used to recreate the right levels of turbulence in the wind flow. Again, using our specialists not only to supervise and advise on the wind tunnel testing, and in this case this was done by John Rees, one of our wind experts internally, but we also had the ability to undertake some CFD analysis of the bridge deck cross section in advance of the wind tunnel testing, and that was particularly useful in terms of advising the performance of the windshields themselves. And here you can see the actual bridge deck cross section being tested along with our simulated high-sided vehicle here, which here this model is being used to measure the overturning moments on the vehicle. And this is the final windshield itself, and I think you'll agree it's nice and transparent, which was one of the key features we were trying to achieve with the windshield. We didn't want to inhibit views from the bridge deck for bridge users. Now, I haven't talked about the other structures on the project, but one of the points I wanted to get over here was the importance of developing a family of structures, and we did this by working very closely with Dissing and Weitling, so that there was a common resemblance throughout the project. You can see here the main crossing on the center image and the two images with the pile on the left, but on the right hand side you can see the family of structures we developed to be used elsewhere on the project, and I think that was a key positive for us. In terms of construction methods, I'm going to talk about some of the foundations. I'm going to talk about the form traveller used for the cable stay bridge, and then finally the movable scaffold system used for the approach viaducts. So very early on in the development of the design, Hugo Wood from our side, one of our leading geotechnical engineers, came up with a proposal to use spread footing foundations for the main pylons, and that was because the sandstone was at relatively shallow depth, as can be seen on this image here. On the north and south approach viaducts, we did in fact have conventional pile foundations, but they were developed by Hugo and his team to be incredibly efficient. Here you can see one of the pylon foundations under construction, and Hugo had to work very hard to convince not only our own contractor but also all of the other key stakeholders, including the end client, that these pylon foundations were feasible, but they offered massive advantages in terms of reducing construction cost and risk, and particularly program, effectively by their simplicity. Here you can see the foundations in a more advanced stage of construction, and finally the casting of the first of the foundation. This shows the cable stay bridge cantilever construction underway, and in fact you can see the movable scaffold system gantry being used to construct both of the approach viaducts on the north and the south end. The cable stay bridge itself was constructed using a fairly conventional system of balanced cantilever construction. That's casting 6 metre long segments, one after the other in a balanced fashion, and that is of course after the pylons have just been erected using a jump form system. We did in fact need to have two temporary towers here and here in order to stabilise the longer of the spans during cantilevering. And this was to show integration of some of the temporary works within the construction of the bridge. Here you can see the temporary pre-stressing, which is used to clamp down the bridge deck onto the pylon head during cantilevering, and this was at both the north and south hammerheads. Here you can see the central pylon under construction, and in fact on the right hand side you can see our Tekla model showing the reinforcement detailing. And back when we were developing these models, these technical models back in 2015 or so, we were still at a relatively early stage, I think, both as a profession and an organisation in terms of what we were doing with these 3D models. But this was fantastically useful because it allowed us to check for clashes before construction progressed. Here you can see the form traveller for the pylon being assembled on top of the cofferdam on the left-hand side. The four arms projecting from the pylon are then used to lift the form traveller up into position, which is what you can see on the centre photograph. And then on the right hand side you can see the pylon at a fairly advanced stage of construction. The pylon was constructed in 5-metre lifts, and wherever possible we prefabricated the reinforcement cages in order to reduce the cycle time. And here you can see one of the cages assembled and being transported out before being lifted in. We actually managed to achieve a cycle time of around 5 days for each pylon segment, which was pretty impressive. And this shows fabrication and assembly of the internal fabricated steel box that's used for the cable anchorages. The cable anchorages, as I mentioned, are relatively conventional, and the key feature here is by prefabricating the steel boxes off-site, it gives us the chance to check the geometry of the stay anchorages in advance of them being lifted up. Just to talk a little bit about the deck construction, here you can see the form traveller cantilever construction just starting out. Here at a slightly more advanced stage of construction, and again all of this was very carefully coordinated in conjunction with the contractor. Construction here is at a much more advanced stage. I should say that the contractor itself consisted of Kia, FCC from Spain, and Samsung, who are probably better known for providing mobile phones and tablets, but a pretty powerful construction joint venture, and that's what you needed for a scheme of this size. Here you can see construction at a more advanced stage. You can see the access jetty, the temporary access jetty that ran all the way across the estuary here, and that was a key feature of providing access for construction. This shows the movable scaffold system. This is basically a 1,400-ton self-propelled gantry which is used to cast the approach viaduct spans. And those spans are actually cast in 3 primary stages. The first stage, stage 1, is cast on the MSS. Stage 2 is the infill slab, and stage 3 are the cantilever wings. And the reason for casting stage 2 and stage 3 separate from the MSS is really to decouple critical path activities. So here you can see the first stage being cut, which is cast on the MSS, the infill span, which is cast using conventional falsework system propped off the bottom slab, and then finally the cantilever wings, which are cast using a completely separate form travel system. This shows the reinforcement cages and pre-stressing having been assembled. These were all prefabricated off-site, typically in 6-metre long bays, before being lifted up and positioned within the MSS. And I like this view particularly because it shows all 3 stages of construction for the approach viaducts. Stage 1 on the MSS, stage 2 is where that infill slab is being cast, and stage 3 is where the cantilever wings are being cast. The bridge was finally opened in October of 2017 to a big fanfare. That's just a little over 5 years ago, and it's been a huge success ever since. Here you can see the bridge a few years after construction was completed, and you can see the salt marshes have recovered, reinstated to their former glory, and the channels, indeed, they haven't been their dynamic behaviour hasn't been inhibited, we believe, based on the monitoring so far. I think this photo also shows the nice clean uncluttered deck that we have. We've contained the signs and the gantries to just the left-hand side there, you can see, and quite discrete signs on the pylons themselves. Those gantries, incidentally, are effectively the tolling machine. They're effectively the cash machine for the project itself. And then in terms of embodied carbon, we're actually really pleased with Mersey Gateway. It scores a B on the Scorps rating, which is very impressive when you think of the span of the bridge. Normally, as the spans get longer, you could justify, or you'd expect anyway, a slightly lower rating, slightly higher embodied carbon, but actually I think this nicely illustrates the efficiency of this design. So in summary here, this is a brilliant example of major bridge design and the integration of construction methodologies. There were many specialists involved. Architectural design was key to the solution in many regards, and it's added enormous value in terms of relieving traffic congestion and promoting regeneration in the area. In terms of co-creation, it was a great example of how we as a unit work very closely with our clients as well as the wider design team and of course the contractor. My penultimate project is really quite different. This is a project in Bangladesh to design foundations for a 400 kilovolt crossing. Now, we first became involved in this Padma project back in 2007 when Ian Firth and I travelled out to Bangladesh to write the terms of reference for the design of the Padma Bridge. We subsequently went on to become the independent design checker for the bridge, and then in 2018 we were invited to prepare the design for this 400 kilovolt line crossing, which is just downstream of the Padma Bridge. And here you start to get a flavour of the scale of the project. The Padma Bridge itself is 6.3 kilometres long. So the real challenge around Padma Bridge is actually around construction of the foundations. You're sitting on extremely poor quality soils with no rock to speak of at any depth. The river itself develops deep scour channels down to minus 47 metres on a 1 in 100 year return period basis. Any foundations in the river are particularly vulnerable to ship impact and seismic effects, given the foundations cantilever from the riverbed. And one of the key drivers behind the particular solution for the 400 kilovolt crossing came from our close collaboration with the contractor. The contractor was a Chinese contractor called MBEC. Having been out on site during the construction of the Padma Bridge, it became evident that the foundation solution was extremely challenging. So conventional foundations for these sorts of crossings really revolve around base grouting the piles, and that's done by casting, in this case, casting a concrete plug down the bottom of a raking pile. And you imagine the challenge of knowing what's happening some 120 meters below water level when you're trying to inject grout to achieve adequate in-bearing capacity. It's extremely problematic, I would say. So having sat with the contractor, one proposal we came up with was actually to drive the piles vertically and to drive them open-ended, such as we can mobilise a level of internal plugging within the piles and thereby avoid the need for base grouting of the piles altogether. Now, the fact the piles were vertical significantly improved the structural performance of the piles, because by making the piles more flexible, actually the forces that they pick up under both seismic and ship impact cases are significantly reduced. We're mobilising effectively the bending capacity of the piles. And then again, calling on our geotechnical experts, in this case Professor Johan Steenfeldt, who I've worked very closely with over a number of years. He managed to develop a sequence of pile installation that enabled this partial plugging to mobilize the base resistance required. And again, that was an example of how we work extremely closely with the contractor to ensure that end objective is achieved. The piles themselves are quite massive. In this case, they're around about 110 meters long, and they weigh of the order of 550 tons each. So they really are quite something. Here you can see one of the platforms on the left, one of the towers on the left at an advanced stage of construction. The one in the middle is obviously finished, and just to give you a flavour for the overall proportions, in this case the pylons are cantilevering around about 190 meters from the riverbed to the very top of the pylons, and then the piles are towed in over 100 meters below water level. My final project today is actually a pair of bridges in Brisbane that forms part of the Green Bridges project promoted by Brisbane City Council. This actually has been one of my most enjoyable projects in recent years, and I think it illustrates a number of the features that I've discussed earlier on. In this case, we worked very closely with Wilkinson Eyre Architects to develop these two designs together with GHD, an Australian consultant. The aspiration here is to have two bridges, Toowong Bridge on the left hand side, bridging across from Toowong Station just to the left there, across to the West End side in the middle, and then St Lucia Bridge over to the right hand side, bridging from the university again over to the West End side. And you can see Brisbane Central Business District in the distance here. So this is the Toowong Bridge. You can see here we've got a single mast that's backward leaning. It's supporting a deck of one side only. And the inspiration for this design came to some extent from the sail bridge which I described earlier on. This is very much a development of a similar structural principle, but it was very much developed to suit this particular site. So on the left hand side you've got the Toowong area, on the right hand side you've got the West End area. One of the key constraints here was to minimise foundations in the river because of the bend you saw earlier on. We wanted to avoid having obstacles that could impair the free movement of quite a significant volume of river traffic here. So there really was a key driver behind going for a cable stay bridge solution. Here you can see a view on the bridge deck. Given the climate in Brisbane, there is a need to provide as much shading as possible, and that's being done by these canopies here, which are all integrated within the design. On the right hand side you can see the stays springing off the bridge deck edge there. And just to put it in context, I've put the sail bridge here in red. The sail bridge is around about 130 meters long overall, and it comfortably fits within the main span of the Toowong Bridge, as you can see here. Toowong Bridge is around about 320 meters long overall. In terms of embodied carbon, this bridge comes out with a rating around about F, but I think, as I alluded to earlier on, it's important to remember that for this bridge type, actually that rating is reasonably good, because we're talking about longer span structures and actually more challenging foundation conditions. And you can see the Scorbs rating up in the top right hand side. Of course, the dominant material here is steel. This is the St Lucia Bridge. This is altogether very different, whereas for Toowong we were quite happy to have a tall mast that drew the eye, as it were. for the St. Lucia setting, we wanted an altogether much more low-key structure that was less visible. However, at St. Lucia, the single biggest constraint are the ramps and the tie-ins at each end. So in the middle of the river, we still need to achieve the same overall clearance, but getting down to the riverbanks and both ends was a real challenge. And working very closely with Wilkins & Eyre, Jim in particular, we came up with this solution where you've got this lovely curving ramp that snakes round. You do also have a stair access going down the middle, as you can see here. And of course, this is a suspension bridge solution, quite a different sort of structure to one. And this is the ramp at the other end. In terms of embodied carbon, this again is very similar to one. We're scoring around about an F. I think quite reasonable given the form of structure and the physical constraints that we face at the bridge site. So in terms of a wrap up, I hope I've presented a few good examples to illustrate the types of projects that we at Covey have been involved in together over a period of around the last 20 years. I've only been able to pick a very small selection of projects, but I hope you found those interesting. I think the key conclusions from my side are that as engineers we're facing increasing numbers of challenges and many more demands placed on us. I think it's really impressive the way we as a profession are responding to those. Cost and program have always been key drivers, but I think more and more these days we're seeing other features pull on our time and our demands. Quality of design, I think, as I've illustrated, is always key, and I think we as engineers have a responsibility to remember that these assets that we're building are multi-generational. They are going to be there for decades to come, and it's really important that we put everything in to finessing those designs. I hope I've illustrated that a number of our designs have come about through that iterative process. Always trying to improve the design as the design evolves. Making our designs durable and maintainable and reducing the whole life cost has to be key for all of us. The environmental impact associated with both the construction phase and the in-service phase are key. In terms of not only the embodied carbon but the whole life carbon, and I think that's going to be the next challenge for us as a profession, looking at not only operational carbon but also looking at how our designs influence the user carbon consumption on our bridges, and that's much more part of an infrastructure type assessment for carbon, embodied carbon. I hope you've enjoyed this talk. I hope it's provided some useful insight in terms of what we within Covey have achieved together, and it's appropriate, of course, to give full credit to the wider Covey team for all of their input to these projects and indeed this presentation. Thank you for listening.